Hello, everyone, and welcome to today's webinar, Taking Control of the Unknown, Nanoparticle Hazard Containment. I am Alexis Krause of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Labconco. To learn more about our sponsor, please visit www.labconco.com. Now, let's get started. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many of your questions as we have time for at the end of the presentation. If you have trouble seeing or hearing the presentation, click on the Support tab found at the top right of the presentation window, or report your problem by clicking on the Ask a Question box located on the far left of your screen. This presentation is educational and thus offers continuing education credit. Please click on the Continuing Education Credits tab located at the top right of the presentation window and follow the process to obtain your credits. I now present today's speaker, David Wasescha, Product Manager at Labconco Corporation. For the complete biography on our speaker, please visit the Biography tab at the top of your screen. David, you may now begin your presentation.
Great. Well, thanks for joining us today. I'm going to talk a little bit about a couple of different things in nano containment. We'll talk a little bit about nano just as a background, and then we'll get into some containment options and how to really assess how those containment options are working and tested. So without further ado, let me just dive right in. So nanotechnology can be defined really by looking at the size of the items that you might be researching, or maybe a process that you're carrying out is producing. But typically we think about nanomaterials as being in the 1 to 100 nanometer range. And these are items or these are materials that are a lot smaller than traditional chemical powders. So if you were to look at the pharmaceutical powder or chemical powder, they're typically going to be significantly larger than nanomaterials. So if we look at some uniqueness of nanomaterials and why there's a concern with handling these types of materials, it's largely based on the amount of surface area that nanomaterials can have. So if you expose more and more surface area by reducing the size of a particle, you're basically creating an interaction with, potential interaction with your body or anything that you come into contact with that's a nanomaterial that has more biologically available space. So a good way to think about this in different concepts is imagine you have a cube that's the size of the room you're sitting in right now. So maybe it's 10 by 20 feet. I guess it'd be a rectangle, but anyway, a large volume. If you were to divide that up into several smaller pieces, you're now exposing the surface area that was formerly hidden within that larger box shape. And if that surface is biologically relevant to your body, perhaps in a negative manner, that can cause an unwanted impact. So imagine that in your lungs, etc. The unique thing about nanomaterials is sometimes they behave very differently than their larger structures. So here's classic example of gold. So gold, the lead brick form or the solid brick form is in a big bar structure and it has a gold appearance. But if you actually nanomaterialize that gold, it's going to look more like the liquid on the right, which is a red solution. So they can behave differently. Items can behave differently when they're produced in nanomaterial sizes. Nanomaterials are also generated from a couple of different sources. So here you'll see a couple of examples of natural versus engineered nanomaterials. So scary thought, but nanomaterials are in environments that we pass through every day. So they're in exhaust, they are produced by wildfires, they're produced by even some organisms produce things that are in the nanomaterial size. But even more so, a focus should be placed on engineered materials, because not only are these nanomaterials in size, but we're forcing properties and and unique features about nanomaterials that may not just be biologically or naturally relevant and could have more increased impact on health to those who might be exposed to these materials. So kind of talked about some of their unique features and their different behaviors. Another important thing to consider is that nanomaterials research is really still in a very budding state of its overall development. So you think about pharmaceutical powders. Well, we've known a lot about different types of drug powders for a long time, but nanomaterials are still very new. People are doing lots of interesting experiments and creating new materials that have not existed prior to current research going on. So that's just an important thing to consider when you're realizing you may be working with something that you don't know the hazards of yet. So a lot of people are generating nanomaterials, but how do we know that they need to be contained? Well, we don't. We don't really know until we have that data. So the best thing that you can do is offer yourself some protection. And so I like to think of my friend Al Pacino here. And if he was, sitting in real life handling hazardous drugs with a giant, amount of them sitting on a table in front of him, obviously that's a risk that he's undertaking that could cause severe health impacts. If you were to sit in front of a pile of nanomaterials, its potential for health implications can be equal to or even more severe. So obviously, Al Pacino needs a hood. Another way to help conceptualize the hazardous nature of particles, whether they're drug particles or nanomaterials, is to look at how potent these items can be to create a toxic effect. So here's a little example that hopefully will help you understand how even a small amount of nanomaterials can be hazardous. So here we're looking at the Empire State Building, and then you've got a 1 gram sweet and low sweetener packet. So if we quantify these, so the Empire State Building is roughly about 1 million cubic meters. In that package, you've got about 1 gram, only a gram of that sweetener or sugar. If you were to imagine yourself standing on top of this building and you open that package up and disperse that tiny little gram into the entire volume of that building, you'd end up with a concentration of sugar at a rating of about 1 microgram per cubic meter. So if you step back away from this example, just imagine for a second trying to see 1 microgram per cubic meter in the air column in front of you. In fact, you can't see it with the naked eye. You have to use a microscope. The naked eye, the human eye, can really only see to about 100 micrograms per cubic meter, and that's with really good resolution and contrast. So that would be a setting with a white powder against a black background and ample lighting. So in reality, in your working environments, most people don't have, a suitable white substance with a black background, so it's even harder to see that. But that's okay. For this example, we're only looking at a microgram per cubic meter, so you certainly can't see it. So, all right, if we look at the occupational exposure limit for carbon nanotubes, this is going to vary depending on some characteristics of the nanotubes, but it falls somewhere between 1 to 50 micrograms per cubic meter. So at a concentration of even higher than that little sugar packet, you're in a situation where you may be experiencing unwanted health effects, and that's just the operational exposure limit. Sometimes, you may be exposed to levels that are much higher, and you're still not going to be able to see them with the naked eye. So there are ways to contain particles, and the best first thing to do is to remove those particles from the air you're breathing. So if we take a fan and we turn it on, we get two things out of this. So we get a negative pressure area behind the fan blade, and then a positive pressure area on the front. And what this exhibits is basically a push-pull effect. So here you've got air behind being pulled towards that fan blade. And once it hits the fan blade, it's going to be pushed or positively pressurized away from that source. So the working force here is the fan blade. And you can imagine if you can pull items toward the fan blade, you're controlling them but once they get on the fan blade's front side, they're pushed out and they kind of go wherever they please. So we like to keep everything under negative pressure when we're going to contain items because we can draw that air towards a source. Well, we know in a laboratory setting that's great to have a fan, but you don't want to just blowing everything around everywhere. So we can mate that fan up with a box, and for the terms of this presentation, we'll call this box a hood or an enclosure. Sometimes you see the words interchanged. In this sense, we'll just approach it from a containment device. So in this hood, you're looking at a side view. You've got an opening on the left where all the air is coming in. That's the opening underneath the glass sash. And you'll notice that the air is entering and kind of curving through some airfoils at the opening and then also at the very top. So all that air is going to come in, and then this is all in the negative pressure side of the hood. The fan is going to be somewhere farther downstream. So air is going to flow into this hood under negative pressure, and this is the environment that you would want to work with nanomaterials in because they're going to be pulled away to the back of the hood from you and then contained. So, all right, well, if we push or if we pull that containment towards the fan, eventually that fan's going to have to be located somewhere where anything going on the other side of the fan is going to be positively pressurized, and then we've lost containment control. So we can add another feature into there, that's a filter. So either a HEPA or Alba filter can be used for nanomaterials, and these are particulate filters. So HEPA is high efficiency particulate air, and Alba is just simply a more dense version of a HEPA filter. And both of them are made of borosilicate glass fibers that are woven into a random weave and then folded into a filter that looks something like what you're seeing on the screen right now. So here you've got an aluminum frame that has a gasket on it, and then all of the filter media to trap all of those particles before they end up somewhere else in the lab or ductwork of your building. So one thing that is important to note when you're looking at these filters is the rating on them. So they all have different types of ratings of filter efficiency. And what that means is it's a rating basically of the weakest point at which that filter can operate. So in this case, we like to call that the most penetrating particle size. And the particle size actually changes depending on the filter density. So with a HEPA filter that's rated for 99.99% efficiency, that's actually its efficiency with particles that are 0.3 micron size. Alba filters are more efficient, and that's actually measured at 0.12 microns in size. So those are the particles that actually are most effective at getting through a filter bed media. So if you have a filter, or if you have a particle size that's larger or smaller than the MPPS value, it's actually going to be trapped more efficiently within the filter. The way that's done is through a couple of different methods that particles interact with the filter media. So you've got inertial, interception, diffusion, and electrostatic attraction. And you can kind of see how particles behave as they're running into these filter media. So a lot of it is done through interception and diffusion. If you have a lighter particle than the MPPS point, so really, really tiny, it's going to likely diffuse because it's so light it's kind of flying all around in the filter media and will impact the fiber. As particles get larger, they're more likely to experience interception and an inertial impact, with electrostatic attraction being pretty rare given the fact that the filter media is borosilicate glass, which oftentimes doesn't retain a very strong charge. Okay, so now you've got a fan, you've got a box, you've got a filter, but that filter is going to contain all of those nanomaterials and other things in the laboratory that will be collected over the life of the filter. So the last thing you want to do is just pull that filter right out into the laboratory. So a really important thing to do is operate under a barrier system between yourself and that filter. The way you can do that is using a bag in, bag out, or BIBO filter system. So here you're seeing technicians who are tasked with changing out a filter from a nano containment hood. And this is basically a system that is more or less a glorified bag that surrounds the filter and provides a physical barrier between yourself and the hazardous contaminants on the hood. This system actually really only exists on hoods that have particulates in use inside the hoods, and that's because particulates, so whether they're chemical powders or nanomaterials or other physical items, they typically have a very difficult time being decontaminated or being made less hazardous. Conversely, if you work in a biological setting and you have bacteria or viruses, those are items that can typically be killed, and once sterilized with something like vaporous hydrogen peroxide, they lose their dangerous characteristics. Not all, but some can be killed that way. So, but when handling nanomaterials, here you are with a physical barrier to keep those dangerous materials intact in the filter and away from yourself. So at this point, a lot of people typically ask me, why not use a fume hood? Well, think for a second about what happens when you turn on a fume hood. Fume hood's controlled by a blower on the rooftop somewhere in your building, and anything that goes through the hood is going to be run through that entire length of ductwork and then pulled into the motor blower and then exhausted through the outside into the air column above the building. Normally, with chemical fumes, chemical vapors, those items are ejected into the airstream and diluted very rapidly. They don't have a physical mass, they're just a chemical vapor that dissipates over time. But with nanomaterials or powders, those are physical items that don't have a way of being dispersed easily. So they end up in bad places. They end up in the ductwork, they end up in the parking lot, they end up in the blower and on the rooftop. All the areas that are where air passes out of the hood and eventually onto are places where there could be contamination. Well, that's not a great use for a fume hood because there's really no way to stop the nanomaterials at any point and contain them. So there are a couple of options. And here are two commonly employed pieces of equipment for nanomaterial handling. On the left, you'll see there's a nano containment hood. This is a hood that has an opening and allows for easy ergonomic work within the area that's containing. There's a filter inside. And you'll see it generally represents what you might know as a fume hood or sometimes a balance enclosure or powder containment hood. The other hood, or the other equipment on this slide, is a glove box. Glove boxes come in a lot of different configurations, but for nanomaterials, the key feature that you would want to see is a box that has a bag in, bag out filtration, either HEPA filters or Alba filters that help to keep everything in the box and prevent it from getting into the room. So let's dive a little bit into the nano containment hood. So first off, you've got a negative pressure environment. That's a controlled airflow area that we know can help contain and trap those hazardous particles that you may be generating during a procedure. So in this cross section, you'll see airflow flowing to the back of the hood, and it's actually driven by a blower. That's that kind of whitish feature in the upper part of the hood, and then onward into a filter. So good things about nano containment hoods are construction of stainless steel, and this lowers the static charge on the surfaces over. Definitely you would not want to use something that's made out of plastic, and also you want something that's going to be easily cleanable. So stainless steel is not particularly porous, and it also stands up to lots of cleaning materials that can help get nano containment materials out of crevices. I mentioned there's a filter, so Alba filters can be the most effective at nanomaterials, and you would certainly want to include a bag in, bag out containment feature for that filter. Another important thing about a hood is to have airfoils and a baffle. So in the back, you'll see that perforated wall. That's actually what it is a false wall, and it helps to maintain airflow distribution through the back of the hood without having to race and speed up the velocity of the air to any one opening at the back. You'll also notice there are airfoils and a baffle at the front, just airfoils at the front. Those are on the top and bottom of the opening, so one serves as an armrest, And then also on the sides, those help to smooth out air as it enters the hood to prevent any kind of turbulence that might induce some escape of particles back towards a user's working area where they're sitting or standing. One other thing that can be nice for nano containment to help with static is to integrate an ionizer. So if you can purchase a device that has an integrated ionizer, you can reduce the static and the strange behaviors that some nanomaterials exhibit. Sometimes they act like gases due to static, and with an ionizer, you can at least help reduce some of that static nature and help the hood contain at a higher level. Another consideration you should take into account is placement of that hood. So this is good practice for any type of hood, whether it's a fume hood, a biosafety cabinet, or a nano containment hood. But you really want to locate this like an open hood away from any kind of source that's generating airflow. So heavy foot traffic areas, doors that open and close during working hours, or even the supply diffusers in the ceiling for air return. Might feel good in the summer, but it also may ruin the containment characteristics of a hood. Also, if you have a very sensitive balance that's helping weigh nanomaterials, you definitely want to stay close to a load-bearing wall, and if you can, be located on a lower floor, or use items such as a marble table or dense materials that can help eliminate building vibration. In some instances, nanohoods are also vented, and this would be in conjunction with an application that uses hazardous chemicals, or perhaps as an added layer of safety. So let's say you have a nanomaterial that's going to be diluted into a chemical. Obviously, you would want to contain that chemical vapor as well, but a HEPA filter or Alba filter inside a hood is only going to stop the particulate matter that you're generating. Any gas vapors or air will go right through that filter, so you need to exhaust that to the outside, or perhaps investigate a carbon filter as well. So let's talk about glove boxes for a brief moment. So obviously the number one thing you'll notice about a glove box is that it's a completely isolated containment chamber. So your access into that opening is through a pass-through on the right or left side sometimes. And once you've got that material into the box, it's effectively sealed and leak tight. So then your operation is carried out through the glove ports on the front, and it can be a little bit cumbersome to work into. So it's really reserved for opportunities in your laboratory or working environment where you have so-called high energy procedures, which are energies where you're moving or mixing or generating a lot more aerosols than you might just typically be carrying out in a smaller open hood. This extra barrier of being completely sealed simply just ensures that even if you were to spill something or create an unwanted level of nanomaterials, that they're going to remain inside that glove box no matter what happens. Also, sometimes can be easy to get in and out of. Say you have a laboratory procedure where you need to get in and out of the box several times to go maintain another experiment or do something else in the laboratory. With a glove box, you can simply leave the gloves, pull your hands out of the gloves and continue an operation somewhere else. So getting into characteristics of glove boxes, you'll notice a lot of similarities. So Alba filters, again, with bag in, bag out capability, allows you to remove those filters when contaminated, but in a safe manner. Also, stainless steels are really important for cleanability, ensuring also that you can get into the corners and crevices of these hoods to clean them is a great way to ensure that you don't leave any nanomaterials behind, which can reduce contamination with another experiment, and also is just a good practice for cleaning the hood. You can integrate ionizing fans into these types of boxes as well. There are a lot of options out there. Certainly investigate when you're buying the box if you can integrate one into that. But you may also find that you are using a balance that came with an ionizer. Another thing is, and this applies for both this hood and also the nano containment hoods that are open, is that glove boxes and hoods for nanomaterials testing should be tested to a standard looking specifically at nano particulate containment. And I'm going to talk a little bit now about a company called NanoSafe and some of the methods that they're employing to help assess containment abilities for these types of engineering controls like hoods and glove boxes. So some questions arose as we started considering building these types of hoods, and so we looked to an expert, and the foremost expert in nano containment hoods right now is NanoSafe. It's run by a gentleman named Matt Hull out of Virginia, and some of the questions, we looked at from a design component of these hoods is, are there any methods that exist right now that are good for assessing nano containment? That's the most important one, obviously. Next one is, if there are ways to do it, can you generate a nano aerosol to replicate real-life experiments as closely as possible? And then, of course, always assessing limitations for that experimentation. So the first thing to look at is, well, what's available right now? And there are a lot of different ways to assess the containment of a hood. When it comes to a chemical fume hood, the first thing you can do is look to ASHRAE 110, which outlines a way to look at a gas produced in the hood and the hood's ability to contain. So you'll see a lot of things on the slide. There's a tracer gas detector located on a mannequin. There's an ejector for the gas. That's the thing on the left front of the hood. And then, of course, you have all of this within a hood. And this is all really excellent for assessing vapor containment of a hood. It uses the ASHRAE 110 method uses a gas called sulfur hexafluoride, but that's a gas and not a nanomaterial. So there is another way to look at nanoparticulates, or pharmaceutical powders, using air sampling devices to measure for particulate escape. But those represent methods that are compatible with chemical identification, which is not always easy to do with nanomaterials. So using a combination of both those concepts, we actually can assess nano containment using some modified components. So obviously, the first thing you need to do is change the gas out for a nanomaterial. Then you have to have a generator that's compatible with the nanomaterial. And also, you want to have an environment that doesn't contribute any background noise to the environment. So with ASHRAE 110, sulfur hexafluoride is used because it's not available within the environment. So it's not naturally producing and can't be a background contaminant. Well, we need to do as close as we can to that concept with nano, but sometimes it's very difficult because there aren't a great breadth of non-hazardous nanomaterials that exist. So we'll get into this in just a brief second, but first let's talk about containment. So assessing the ability for the hood to contain has to be done using a device that measures. So instead of using a gas sensor, we actually have to use a nanoparticle size measurement device. And so here's one of the most devices that was used by NanoSafe and is still used. Obviously, with the changes in NanoSafe, nanomaterials constantly going on, there are other options out there. This is a schematic of the operating method for the device, looking at particle size. And I'll actually leave this to, if you want to ask questions about this, I'll provide the contact information at the end of this webinar for Matt Hull and also for NanoScan. But a little bit different than an ASHRAE 110 gas detection method. I also mentioned troubles with eliminating background noise. So in this test, we used silicon dioxide, and that's easy to generate and relatively safe, but it sometimes is available in the environment. So to test a hood, you need to eliminate that background noise, and to do that is easily done in the clean room. Clean rooms are obviously not going to be accessible in every environment where a laboratory nanomaterial hood or glove box is in place, but certainly for the sake of testing on an initial basis, these are important characteristics to take into consideration. All right, so now that we've outlined some of the unique parameters, let's talk about the test material. So here's silicon dioxide, and one of the most important things to do is hone in on the particle size generated in the environment, because our detection system is really looking for particle size, not for the chemical properties within that silicon dioxide. So here's a sample setup of a hood undergoing a NanoSafe test, and you'll see here on this graph that there's a mean particle size of the silicon dioxide that was pretty stable throughout test methods carried out with this particular hood. So concentration is important, and as you see, very stable numbers on the particle diameter. So we know that whatever the particle counter is looking at is truly what we're hoping, or what we're generating as a test aerosol with the silicon dioxide. So in the hood, we want to see lots and lots and lots of particles, because we're generating silicon dioxide out of this ejector. And in fact, if you look at the distribution of particles, you'll notice that coming out of that aerosol generator, you're going to get a significant amount of particles. So this is number of particles per cubic centimeter, and you're in the range of about 100,000 particles per cubic meter in the upper area of the hood. Lower area of the hood is experiencing quite a bit less particles, and that's because of simply just the ejector position. So you'll notice here, ejectors emitting out of the top of that device, and so we expect the numbers of particles to be higher up high. So that's good to see, but we want to know how well this hood contains. So we can look at the number of particles per cubic centimeter as well on the outside of the hood. And so here's some data representative of what was measured outside of the hood, both in the background noise and also at the sash opening, right where you're breathing. Obviously, you want to make sure that whatever you're doing is not coming out of the hood where you're breathing. And so if you compare these numbers, you'll see the background noise is actually nearly identical to what was measured at the sash opening of this hood. So we know that we're containing and not experiencing escape from the hood of these nanomaterials. So they're effectively being captured onto the Alba filter within the hood and not being re-entered into the room. So here's just a summary of the data. So you're looking at a common aerosol diameter. So we know that what we're generating is what's being measured. And then just a quick look at the particles being generated inside the hood versus outside. So we can assess basically a worst case containment rating of about 99.99% effectiveness using a hood containing nanomaterials. As with any good experimentation, it's important to consider some of the limitations. So first one is that without further biological data and health data, it's really difficult to assess the toxicity and exposure level acceptability for various nanomaterials. Even with some very common drugs that you might take over your lifetime, some of those drugs have a limitedly known exposure limit. Nanomaterials oftentimes are very novel, and because of that, there's not a lot of investigation into the health implications. So if you can take steps to just simply evacuate those particles from your breathing area, that's the best possible thing you can do without knowing the toxicity of those components. Another important thing to do is it's hard to test for all nanomaterials. So we use silicon dioxide because it's easy to generate and also easy to measure. Nanomaterials sometimes behave very uniquely, as we discussed. They have different physical characteristics that make them hard to contain, hard to analyze, and so it can be difficult to adapt this test to every type of material you may be using. Kind of covered this already. Hard to know how dangerous stuff is without more data. And also, unlike the drug industry, nanomaterials typically don't have the burden of health and safety when they're generated. So obviously, the FDA in the United States regulates the toxicity and information that on how a drug operates. But if you're manufacturing a component for a computer and there's a generation of a nanoparticulate, you may not have the same burden of safety to a governmental organization like you may have with a drug submitted through the FDA. And also to that, and there's not really a good regulatory guidance on how to behave with nanomaterials. There are information publications out there. NIOSH has nanomaterials handling guidelines, but certainly could always be more information out there. So with that, the best thing you can look at is containing those procedures as best as you can until further information is made available. And with that, I'm going to open it up to some questions. Hope you all enjoyed the presentation, and certainly ask that you ask any questions now during this live period, and if you have other questions after we're done, you can also send them to us via email and we'll answer them individually.
Thank you, David, for your informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on the Answer a Question box located on the far left of your screen, and we'll answer as many of your questions as we have time for. So let's get started. Our first question is, we're currently using a fume hood for a process that generates nanoparticulates. Is there a way to make our fume hood suitable for nanoparticle containment?
So that's a great question. Obviously every lab has a lot of stuff in it already. I don't think I've seen a lab recently that has a lot of extra space on hand. So if your only option for any kind of containment versus open bench as a fume hood, the first thing you want to do is assess if you can make such a modification. And one consideration that you might be able to adapt is to add a filter in the ductwork. There are some manufacturers out there who provide in ductwork HEPA and Alba filtration options. But I would caution against using this as a primary fix for your fume hood, because you have to also consider that any distance between where you're generating particulates and where that filter is located is now going to be a contaminated space. So imagine for a second that you're generating particulates and the filter is located somewhere 100 feet into the duct run. Anytime that filter is modified or adjusted or cut or changed in the future, it's got to be treated as if it's contaminated with nanomaterials. So it's especially important to see if you can trap particulates on a filter as close to the source where they're generated as possible.
Now, David, our next question, are these containment measures specific to types of nanoparticles, or are they for all types of nanoparticles?
They are generally specific, they are generally applicable to all nanocontainment nanoparticulates. Although, there are some that behave very uniquely, some that are also air sensitive. So there are alternate containment options. There are glove boxes that can be completely flushed of all oxygen and moisture and still contain. So I would say if you're handling a relatively inert, simplistic nanomaterial, carbon nanotubes, et cetera, those are good fits for hoods with airflow. But if you have something very unique that has additional dangers, I'd say it's best to talk with your safety staff first and then get in touch with someone like ourselves to discuss potentials for containment.
Do all nano hoods need to be externally vented?
I would say generally most are not, actually. But the driving force there is really, one, if you have chemical vapors or things that would not be trapped by the HEPA or Alba filter, that would be items that are in addition to the nanoparticulates that you're using. That would be case number one, where you would not, or where you might consider an exhaust for a hood. The other one is perhaps your safety personnel on site want some additional protection. So let's say you moved the hood or damaged the HEPA filter inadvertently and had not had it retested yet. If the hood was used and then exhausted, you could potentially place an induct HEPA filtration or Alba filtration to act as a redundant filter.
Now, are there any drawbacks to using Alba filters?
Alba filters, so they're really similar to a HEPA filter. They're just more dense material, and in doing that, you're providing an additional level of protection, but they also require more airflow force to go through that filter. So if you have a very messy application with lots of powder, just be prepared to change that filter more frequently. Another thing about that is if you have nanomaterials that are on the larger side of things, closer to the 0.3 micron range, you might consider using a HEPA filter, as the HEPA filter will still provide protection for those larger particles at a highly efficient rate and may afford you some longer filter life.
Now, David, our next question is going to be does have two parts. So, how about the biopolymeric nanoparticles, and can they be trapped by these containment methods?
Good question. And actually, if you don't mind, I'm going to retain that question to be answered by Matt Hull. Matt wasn't able to join us today, but is a nano containment expert. And if that's okay, I'll just defer that question to him and have him follow up via email.
Perfect. So let's continue on. Let's continue on with our next one. Now, is there a good way to measure for nanoparticles in our lab environment?
Yeah. So you can get a particle counter specific for nanomaterial size constituents. I discussed one option. There are lots and lots of manufacturers out there who make particle counters for the nanoscale items. And I would say if you don't have one in your laboratory right now and you're doing a lot of nano work, you should contact a safety person on site and consider maybe doing an assessment either with an outside party on a case-by-case basis, or perhaps just purchasing one of those yourself for as much testing as you need to control and carry out on site. They're not exactly cheap though, I will caution that. So it's an investment to consider versus having a third party measure and provide assessments for yourself.
And it looks like that is all the time that we have for today. So thank you, David. Do you have any final comments for our audience?
No, I want to thank everybody for joining us today. And I know there are a couple questions that we'll leave to answer from Matt Hull. I seriously advise all of you to go and check out the NanoSafe website. He's offering a very nice approach to consider measuring and doing assessments for nano containment. And if you have questions about procedures in your laboratory or working environment right now, he would certainly be one of the foremost experts to contact and discuss those applications with.
Thank you again, David, for your time today and your important research. We would also like to thank LabRoots and our sponsor, Labconco, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions that we did not have time for today and those submitted during the on-demand period will be addressed by the speaker via the contact information that you provided at the time of registration. This webcast can be viewed on demand through June of 2019. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, goodbye.